excited to be featuring Nassim Haramein here in Canada first. And I watched his presentation in Montreal yesterday, and I can't wait to watch it again because it's one of those things, one of those fields of study, wrapping your mind around these concepts. It's just awesome to keep revisiting it. So without further ado, The Connected Universe. All right, so Nassim's going to talk a little bit more about the upcoming film that's going to document his work. And there may be some of you in the audience that may not have heard of Nassim's work in the Resonance Project. Anybody? Oh, wow, okay, so we're good. All right, but I got to do the man justice. He's been doing this for a long time. And for those of you who might not have heard his background, Nassim was born in Geneva, Switzerland back in 1962. And as early as 9 years old, he was already discovering universal dynamics of matter and energy, which led him on a journey towards pioneering a new approach to quantum gravity and continual developments in unified field theory. He actually grew up in Eastern Canada with an innate reverence for the design of nature and a determination to discover the basic building blocks of creation. Nassim's dedicated most of his time to his independent investigation of physics, geometry, chemistry, biology, consciousness, archaeology, and various world religions. He's clearly a man after my own heart here. His dedication to scientific exploration, combined with his keen observation of the behavior of nature, led him to a specific geometric pattern, which is the core of his approach and new perspective in unified field theory. He's fluent in both French and English, and he's been delivering lectures and seminars on unification theory for over 20 years worldwide. In 2003, he founded the Resonance Project Foundation, and as its director of research, leads teams of physicists, electrical engineers, mathematicians, and other scientists to explore the frontier of unification principles and their implications. Nassim's lifelong vision of applied unified physics to create positive change in the world today is reflected in the mission of the Resonance Project Foundation, and he shares the developments of his research through the scientific publications and educational offerings through the Resonance Academy. So let's give a warm Toronto welcome to the one and only Nassim Haramein, ladies and gentlemen.
Hi, everybody. Hi. Thank you. Thank you. Thank you so much. It's great to be here. Wow, it's my first talk in Toronto. Hopefully not. So I'm excited to share this presentation with you. I've been kind of going around, you know, I was in my cave in my lab, kind of cooped up for almost 3 years, and I just started to tour again. I was in Paris a few weeks ago, in Belgium, and Montreal yesterday, and you know, it's remarkable the response I'm getting, but as well, you know, where are people at and how much, I mean, engineers, scientists from all flux of life are like coming to this, and it's amazing the momentum behind it. And why is there such a momentum? I mean, the Connected Universe movie, I believe, got the best crowdfunding result in history of Indiegogo. Remarkable. We needed to raise funds to improve some of the, to put and improve some of the animations in the movie. And I mean, this movie is going to be incredible. And it's due to your generosity. So thank you so much, everybody, for participating and being involved. And it's exciting to see. I want to present to you today this view of the connected universe that's emerging in science, because it says a lot. It says tomes about who we are, the universe we live in, and how we interact with it. And most people think of this kind of stuff as stuff that is kind of woo-woo, and it's kind of nice philosophical idea that we're all one and all this stuff. But actually, the physics are now showing us that it's really actually the way things work. And that you can take these concepts, write the physics, and get very accurate, very fundamental understandings of the forces of nature and the material world in it. And it's exciting as well, because it not only unifies the forces of physics, but it unifies the concepts that are typically polarized between spirituality and science, which, you know, all of a sudden comes together where you realize that the material world is actually an expression of what we call the spiritual world, or that what we call spirituality is actually the physics we haven't quite understood yet. And so this is really, really critical, because it has the potential to launch our society into a whole new way of interacting with nature. So you can think of the universe as the standard model, and you know, the mainstream scientific community typically think of as this random entropic system that always moves towards disorder, and that where things happens by chance, and literally quantum theory is written in such a way that it is a statistical analysis of the probabilities. Or you can actually, from observation, come to different opinion about the universe. Because the mere fact that we observe the biosphere all around us, and the complexity of even just our being in the biosphere, kind of points to a universe completely different than that one. Because this complexity and this very advanced, you know, systems that we see in the bioorganisms and in the biosphere systems does not point to a random, you know, entropic behavior of nature. It actually points to something that's highly organized, highly communicative, like that is talking very much so, and that is highly coherent, and that strive for coherency, for complexity, that moves towards complexity and advanced systems. And so how we reconcile these two views? Well, let's assume that we think of the universe a little differently. There's a reason why the mainstream scientific community is insisting that the universe is random philosophically, and that there is no organizing systems, is because they have been for a very long time trying to get away from religions and dogma, you know. And so the idea that you know, when you start talking about there's organization in the universe and so on, the tendency is to think, oh my God, he's gonna start talking about God organizing the world or religions, and that's what science wanted to get away from. And in doing so, they've created their own dogma. And that is not necessarily an appropriate scientific approach. That is, as you discover that there is incredible complexity, and that mathematically the concept that the universe is random doesn't actually work out, you should start looking for alternatives. So there's an alternative to going to some religious beliefs, but as well understanding that the universe may be much more advanced in its capacity to relate to itself than previously believed. That it's not just a big boom that happened and somehow miraculously we got here, right? And we'll talk about that. It would be really miraculous, right? So a unified view of the universe. If the universe is unified, what does it look like? And how, I mean, this is what I wanted to know. It's like when I was young and I was in nature, and I'm a sport jock, you know, I'm like crazy on sports. I used to be a ski coach and a ski instructor for many, many years. I'm a climber, I'm a backcountry skier, I'm a scuba diver, I surf big waves in Hawaii all winter long, you know. I'm into it, right? And I'm in nature, and when I look at nature, I look at this incredible thing that's happening, this incredible miracle that's happening, and to me, it seemed unified, you know? Like the bee somehow knows that it's got to go to the flower, and it knows how to deal with that flower so that there's more flowers that happens, and you know, and the whole system and everything is just tuned perfectly so that all this stuff happen. And literally this is called the fine-tuning problem in physics, okay? It's funny because it's called a fine-tuning problem, but it's not a fine-tuning problem, meaning it's like a big problem, right? Because the fine-tuning problem is that, like, if the electromagnetic field in the universe was just a little different and the gravity was a little bit different, you know, like anything, anywhere, in any shape, a little bit different, none of this would happen. Like it would all just go, you know, like it just wouldn't happen. And so it's kind of puzzling, like, okay, why is it like actually tuned perfectly for this to be happening, right? And, you know, there's views where, which I think is kind of a like way to avoid the issue, saying, oh, well, there's infinite parallel universes and we just happen to be in the one that's tuned perfectly. All the rest are like a big mess. Okay. Well, other than that view, maybe there's another thing that, like, it's tuned perfectly because it actually knows what works and what doesn't work, right? Maybe it's actually talking to itself. Maybe there's feedback. Maybe, you know, the fact that we see feedback everywhere in nature is actually because it's an expression of what's happening at the much fundamental level in the material sciences, in the physics. Maybe there's feedbacks in the physics. Maybe there's something talking to something in physics, right? Maybe it actually knows what it's doing. And maybe the fact that consciousness somehow is present is not just some random events that's kind of like miraculously happened, but it's fundamental to the way things are. So, you know, I kind of got lost. I have a presentation to give. You know, we gotta have tea one day and talk about this. But this division in our thinking, this idea that things are isolated, things, you know, that we can observe something over here and ignore the rest of the stuff as if that thing was separate from that thing over there, is present everywhere in our society. And, you know, even in our physics, we have that. Meaning the standard physics we have today have this big separation in it. Cosmological physics basically is dealt with Einstein field equation that describes the gravity at the levels of galaxy and stars and universes and, you know, quasars and planets and this stuff. And quantum theory, on the other hand, describes the subatomic particles, the atomic structure, even the molecular structure at the very fine level. And the two don't agree. They don't agree at all. Einstein field equation describes the universe as this space-time metric that is smooth and curving to produce gravity. Like Einstein described gravity as like if you put a ball, if you put a mass, right? So it's part of the equation, mass producing curvature. So if you put a mass on a structure like a trampoline and it curves that trampoline, another ball would appear to be attracted, right? And but he didn't say actually, and this is why we actually don't exactly know what gravity is, he didn't say what space-time exactly is. So, you know, that doesn't, all right? But it says it's smooth, right? The equation says it's very, very smooth. And if you look on the quantum side, when we look at particles and how we express the physics of particles, we're finding that at the quantum level, everything is quantized. It's very defined, you know, linear functions that make boundary condition. And so it's granular, so it's not smooth at all. And so the two don't agree. And for, you know, all of his life, Einstein, after writing relativity, tried to find a way to solve unification, to bring gravity into quantum physics and find a way to describe gravity in a way that would work for bounded states of quantas of quantum physics. And literally all his life he worked on it. I mean, literally hours before his death, he was trying to solve this, right? And then something he said that was really important, he said, and I quoted that in my latest paper, he said, when we find the solution, most likely it's going to be really simple, it's going to be geometric and algebraic in nature, you know, like it'll be geometry. Because Einstein was strong on geometry, he's well known for having geometrized space-time, right? So the two don't agree. We have this split, but it's not just in physics that we have this split. You know, there's many ways we can look at this split in our society. For instance, men and women. You know, men typically think in bounded linear states, right? Like finite function, right? Like they do one thing and then they do another thing, you know. Women tend to think in more open, like infinity kind of thing, you know. They can like have the baby on the hip, you know, with the milk and, you know, text at the same time, and with their toe they're doing the dishes, and it's like, no worries, right? Kind of separate way. And you know, that division happens in many different ways in our society. So it's really fundamental in one way. It is similar to the division between spirituality and science. You know, like science tend to think in very bounded, linear way. Spirituality thinks in kind of infinities, you know, kind of way. And so the two don't agree. But the thing is And that kind of, you know, when I used to go to physics conference some 25 years ago, and I would talk to physicists and give my presentation and kind of dodge tomatoes, I would, you know, I would always be surprised because some physicists, and that was the opinion of most physicists at the time, and it's just because they were told that as students, so they just repeated it. But their idea is like, well, it's okay to have two physics. There's no need to try to unify them. You know, we just have physics for the big stuff and physics for the small stuff, and that's the way the universe works. And then I'd be like, but wait, that's hurting my brain, brah. Because like, the big stuff is made out of the little stuff. So how is it that like, where exactly does the universe change the equation? You know, in between the big stuff and the little small stuff? Like, where is, you know, that kind of doesn't work. And, you know, usually the response I got after that was like, well, if Einstein didn't figure it out, like, you know. Dude, you know. Give it up, brah. Thing is that Einstein didn't have the mathematical tools or, you know, necessarily the data that we have today about what we're finding out in the universe and what we're finding out at the quantum level. So, you know, it would have been harder for him to put it together, a lot harder. And, you know, and as well, Einstein never agreed with some of the fundamental principles of quantum theory, and so he was pushed aside very quickly after writing Relativity. So it was kind of difficult for him to get that. But today is a different, it's a different world. And today we've drilled down into, you know, galaxies and stellar objects and atoms. And as we drill down on both sides of these equations, we reach very interesting points. And so when I was doing all this, you know, I was like a heretic, you know, living in a van by myself, isolated. And so I was thinking there must be a connecting point. Like, can I find a place where Einstein's equation kind of meets quantum theory? Like, is there something that connects the two? How, you know, if I could find something, just one thing that I can find in both places, then that might be the link that I could, you know, eventually find a unified view from. And I realized when I was studying black holes that Einstein predicts black holes. Right? Meaning that Einstein general relativity equation for gravity predicts, you know, a singularity, a point of infinite density in the middle of the black hole. Meaning that space-time is curving to infinity in that place. And I want to mention something really important, is that those equations are used every day by scientists, right, astrophysicists mostly, to describe orbitals or to describe masses of objects in the universe and so on, all the time. And every time they do, they actually describe that mass, they actually describe that object as a black hole. But they don't necessarily pay attention to that. Meaning that if they want to, you know, describe the sun or, you know, the moon or the planet orbiting around the sun, and they want to, you know, calculate the orbits and all this stuff, they start by solving Einstein field equation. They start by solving the Schwarzschild solution, is the solution to Einstein that predicts black holes. They solve that for the sun, and they solve that for the Earth, and then they looked at the orbital relationship between the two. So they've made the sun into a black hole, and they made the Earth into a black hole, but only mathematically, right? And then they describe, they can calculate all the stuff that these objects are doing. But in some ways, not realizing that they've done this. That they've used an equation that says in the center of this gravitational field that you just described, there's a point of singularity, a point of infinite density, right? And because what we do in physics is we only look at the gravity where it's weak, not where it's very, very strong, right? Only where it's strong near black holes, where we say, well, that is a black hole we're observing. So not to confuse you, when I looked at this, I started to realize, well, wait a second. When they do this, they get infinity. And from quantum theory, I knew that when we drilled below the nucleon of an atom, when we went further and further and further, we reached what's called quantum field theory, where not only the particles are quantized, but the electromagnetic field is quantized. And there, the equation as well says there's an infinite amount of energy in every point in space. And I'm like, wait, I got two infinities. I've got two singularities. Maybe this is the connective tissue. Maybe this is where, the two come together. Maybe I can extrapolate the gravitational effect, the singularity of a black hole, out of the vacuum energy infinities at the quantum level, at the very fine level. And in both cases, the equations are renormalized, or there's a cutoff value that's used, so that it's not an infinity in the equation, but it's actually what's called the Planck length. So the two lead directly to the Planck length. And the Planck length is a little electromagnetic fluctuation of 10 to the minus 33 centimeters. So it's teeny, teeny, teeny. That's the wavelength of this oscillator. And it's present everywhere. But basically, this is the cutoff value that was given for the black hole and for quantum field theory. So I know I've lost a whole bunch of you out already. All I'm trying to tell you right now, we're going to drill into this and you'll understand it. It's not that complex. But all I'm trying to tell you is that this little entity, this 10 to the minus 33 thing, this little oscillator, okay, seems to be present in both theories, okay? And it might be the connected dot, literally, of the two. You see, if you were to start, instead of everything is disconnected and everything is independent from each other, to a theory where everything is connected, then you'd have to say, okay, well, what's connecting everything? What is present everywhere that makes it possible for everything to be connected, right? How is it all connected? Because it doesn't appear to be connected in our daily life, other than in the laboratory where we see that particles seems to be entangled. So if you thought of all the things that could connect everything, eventually you would get to this. The only thing you can find everywhere is space, right? Because we have space between galaxies, we have space between planets, stars, all this stuff, there's space everywhere. And if you look at the atomic level, if you take the densest, molecule, like carbon, like diamond, if you grew one of the atoms in that molecule so it's an orange, the other orange would be like 2 football fields away. So there's a lot of space there too. And even the atom has 99.99999% space. I think I got a laser, yeah. And so space is everywhere. And I think this is really significant because you get these spiritual people all the time saying, well, it's so dense down here. And it's like, dude, it's 99.9999999% space. What do you mean? But we pay a lot of attention to the 0.00001%, right? Because we think of that as our reality. Like, in fact, all you have is space that's wiggling a little bit, right? And we call that a reality, and like, you know, we think, oh, all we're touching here is a little solid space. Right? I think, like, actually nothing has ever, I mean, that might be disconcerting for your partner, but nothing has ever touched anything. I mean, literally, huh? Not even close. All you have is like electrostatic fields that are interacting with each other. It's like bouncing off each other, but it's not touching. And in fact, if you were like trying to define the concept of touching, you'd have to have something, and you can't actually find anything. Nothing. Meaning, like, the nucleus of an atom, which is like the heart of the atom, the mass of the atom, like, if you look in it, like, if you look at the proton, we call, for instance, the radius of the proton the charge radius of the proton, because all we can say is that in that region of space, there's more charge than in that region beside it. Like, there is density charge in that region, we call that a particle. But it's not a billiard ball, like, hanging out, you know, not. And even physicists are typically confused about that, because they build huge things to like collide these billiard balls to get smaller billiard balls, and then smaller billiard balls. But you see, your physical body is made out of those things. So when you think of yourself, do you actually think of your 99.999999% space? Probably not. So it appeared to me very early that maybe it's the space that defines matter, not matter that defines the space. Maybe we should pay attention to the 99.99999% instead of the 0.00001%. Because, I mean, if that space is actually something instead of nothing, maybe it's just the space dividing that makes it so that there's a little jiggle that we call matter in it. You guys see what I mean? Well, you might say, well, what do you mean the space is something instead of nothing? Well, you know, you typically think of the space between us as empty. You might think, okay, well, there's a little bit of air in it, like a little molecules of air, but generally it's empty. But is that true? No, it's only empty to your perception of the space. I mean, if I brought certain instruments in here to measure the electromagnetic radiation in this room, it would be far from being empty, right? This room is full of X-rays, radio waves, even gamma ray from galactic, you know, cosmic gamma rays. And I mean, like, there's all sorts of stuff going on in here. There's all the radio station with the radio waves and all this stuff. And the fact is that even if you just took a little radio box, you could just tune the little crystal, and all of a sudden you hear the announcer in there. Is the announcer in the box? No. Are you typically conscious that there is an announcer or there's music on the radio waves in the room right now without the little crystal tuned to it? No. But you could actually think of your brain and your nervous system exactly as this radio set tuned to a very specific channel that you call you, if there's information in the space, right? So of course, you're not necessarily, you know, I always say, like, looking for consciousness in the brain is like looking for the announcer in the box, just not in there. So if you were to, like, all of a sudden get that, because you see, you can pick up the radio waves with this little box. You can pick up the electromagnetic spectrum with this other little box. You can pick up all this stuff. But imagine if, I mean, you're not experiencing it directly every second of the day, but imagine that there is fluctuation of the electromagnetic field, that there's information riding on an electromagnetic wave that's way below, way smaller wavelength, way higher frequency, right, than anything we can pick up with all these cool boxes we've developed in the last 100 years, right? Just like before we had any idea that X-rays were there, we thought there was only the visible spectrum of the electromagnetic field. We had nothing to detect any wavelength other than that, other than our eyes. And then we figured it out, right? Mostly by errors. You know, somebody forgot a little uranium near, you know, photographic plates, and all of a sudden it's like, oh, wait, there's something going on. You guys following me? So this stuff is happening at a really small level of existence. How small? I know I can't do that. Okay. Well, you know, I'm not the only one that have talked about space that way. Actually, some of the greatest thinkers on our planet, some of the best scientists on our planet, made very, very profound statement about space. So I'm not like way out there in left field, okay? Actually, I am, but I'm in good company. I like the left, you know, it's kind of nice. The right too, you know. It's all in balance. What's that? You have company. Yeah, I have company. And these guys were mostly ignored on that subject, you know. The world tends to take what they like and not necessarily what they don't understand. So, for instance, John Archibald Wheeler, a collaborator to Einstein, you know, really amazing guy, probably the best physicist ever, I consider, for me. No point is more central than this, that empty space is not empty. It is the seat of some of the most violent physics. Actually, Wheeler theoretically got to the point where he kind of thought that the structure of space-time at the quantum level, at the very fine level, at the Planck size, is riddled with wormholes and black holes, and a very small one, and it's like fluctuating like crazy. Because that's what his equations were telling him. Those guys don't make statements like that if they have no physics to back it up. Just so you know, they're not just talking philosophically, and we'll see why they were able to make those statements. David Bohm, space is not empty, it's full. The universe is not separate from this cosmic sea of energy. Space is not empty, it's full. Of course it's full. We know it's full, even at the electromagnetic spectrum that we can measure, right? Einstein, physical objects are not in space, but these objects are spatially extended, saying that an object
is not like something that's just sitting in the space, but actually an object is space extending itself, making itself visible, making itself something we experience. Okay, at certain frequency, it becomes an object. In this way, the concept of empty space, loses its meaning. So some of the greatest thinkers were very much so on the trail of figuring out what is that thing we call space. And is it something fundamental to creation? Well, I assure you that if it's 99.999999999% of everything we see, it's most likely important. Right? Okay. Well, when the reason why these people were able to make these statements is, as I was saying earlier, when we came up with quantum theory, did you all know that quantum theory emerged because of a light bulb? You didn't know that, right? Actually, Max Planck, considered the father of quantum theory, was commissioned by light bulb company to make a better light bulb. I mean, that's how it started. And as you know, of course, he looked at the element in the light bulb and he said, well, I've got to figure out, calculate what's the heat, what's the radiation coming off the element to try to improve it. And when he used the classical theory of the time to like calculate that, the answer was an infinite amount of ultraviolet. It's called the ultraviolet catastrophe. And in laboratory, we don't measure an infinite amount of ultraviolet, so it was wrong, and people were trying to find solutions to that. And he tried to figure it out, and as he tried to figure it out, he figured out something. He found that if he added this little fudge factor in his equations, in the classical equations, he would get the right answer. So he calculated exactly what that fudge factor should be, and when he got it, right, he published it, but he published it saying, this is really kind of yucky, I don't like this physics really, because it was counterintuitive, because the physics were saying when you're boiling water, it's not boiling smoothly to a temperature, it's going through these little quantas of energy that were that value that he had to keep putting in. And that became the Planck's constant. Because it was eventually found that actually that's kind of fundamental to how the universe does things at the quantum level, that an electron in an electron cloud will, you keep putting energy, will only jump to the next level when it reaches that Planck energy level, and it will just go in quantas. It won't smoothly go from one shell to the other. It will only jump to those very specific integers. And this is why it was contrary to what Einstein was saying, because Einstein was saying space-time is smooth. Even at that level, it should be smooth. It ain't smooth. It's integers. And so that was all cool, that was all good, but then that meant, and Einstein used that to write his paper on the photoelectric effect, which got him the Nobel Prize. They had to give him a PhD first, and then they had, and he, I think he coined the word photon, and the little particle of light. But that was all good, except that when they extrapolated the theory to the electromagnetic field as a whole, something didn't work. That is, the equation said that the electromagnetic field was composed of these little quantas everywhere, but these quantas were going to infinity, meaning there was an infinite amount of quantas, meaning they couldn't find the end of the electromagnetic field in the structure of space. When they went to the structure of space-time at the quantum level, what Einstein had described at the cosmological level, the equation was saying there was infinities in every point in space. Every point in space was a black hole. But they didn't think of it that way because black hole hadn't been found yet. Einstein didn't have that luxury. He thought actually his equation that predicted black hole needed to be ignored. That part needed to be ignored, that, you know, these things probably don't exist. But now we know they exist because we see them in the universe. So quantum field theory predicted an infinite amount of energy, but that's kind of uncomfortable. I guarantee you it made a lot of people uncomfortable at the time. Because, you know, infinities in physics are kind of like not so accepted. I mean, an infinitely small number is easy. You just ignore it. You know, an infinitely small quantity, you just say, it's infinitely small. It doesn't matter. Right? But when the equation tells you it's an infinitely large quantity, especially of energy, it's like, oh, what do we do with that? Right? And so physicists said, well, let's try to figure out, like, actually, maybe, you know, there's a cutoff to the smallest thing that your universe can do in electromagnetic fields, meaning since they had the Planck length, the Planck constant, they could extrapolate the length, like what is the length of the Planck constant? What is the, you know, the wavelength of the smallest thing the universe could do, the minimum quanta, the minimum photon. And so they used the Planck length. They said, okay, we're going to cut it off there at 10 to the minus 33 centimeters. Now, do I think that the universe doesn't do anything smaller than that? Absolutely not. I think there's sub-Planckian scales. But I think that the Planck scale is a very important pixel size for our universe. And you'll see my equation proves that. It is critical to the way our universe functions. And it has to do as a harmonic relationship to the size of our universe. That is, it's the size of the Planck length because the universe is the size it is. It's a pixel size that makes up our universe. So how small is the Planck length? I forget, I can't click this because it won't go. Okay, so, I'm sorry. Things have gone awry. Okay, so let's start with the Vatican Dome for like something that we can relate to. Anybody here been to the Vatican? Yeah, it's a big dome, right? About 42 meters. Okay, when you're in the middle, you're like a little thing, you know, in this huge dome. And because the staff at the Resonance Project are extremely dedicated to my presentations, I asked Susan to climb up there. She's amazing, huh? And Susan, like most of us, is made out of approximately 100 trillion cells. So I'm trying to give you an idea of scale. Okay? 100 trillion cells. That's what you're made of. Cells are, you know, we think of cells as pretty big because we see them in the microscope. But they're pretty small because there's 100 trillion of them. It's a non-trivial event. And, you know, there's 100 trillion of them, and, you know, you tend to say, oh, I'm one person. Well, there's 100 trillion entities that disagree with that whole statement. Okay? And so 100 trillion cells are hanging out making you dividing at millions of division per minute, okay, with like billions of chemical change every second to make the whole thing work, like clockwork, for like years after years after years after years. This is what you're actually made of. And we have an idea that this is all happening randomly. Okay? I don't think so. In fact, in the paper that we just delivered at the physics conference, science conference in Barcelona, we calculated with the help of William Brown and Dr. Waldbaker the probability for even just the simple, single cell system, like really simple, receptor sites to come together to produce like the most fundamental principle of life. And like, what were the chance in like some kind of Big Bang random thing universe, Dr. Rauscher called it the dead horse universe, it's kind of dying kind of thing. What the probabilities are, and the probabilities are that even just for that first little spark of life to happen, you would need 10 to the 8,896, wrong before you got it right. Right? Okay, just to give you an idea of that number, which is completely irrational in any time period, like 13.7 billion years since the Big Bang just doesn't do it, like you're needing billions and billions of years more. The radius of our universe is a big universe. In centimeters are small, is about 10 to the 28 centimeters. Okay? That's the number of centimeters that makes up the radius of our universe. So that gives you an idea. 10 to the 8,896 probabilities is a lot. Okay? And so you're made out of those 100 trillion cells, miraculously, randomly adjacent to each other, happy to collaborate. And each one of them is made out of 100 trillion atoms. So are you starting to get a sense of scale? Okay, you're made of 100 trillion cells. Each one is made of 100 trillion atoms, so the atom is already extremely small, right? Okay, now if in the middle of that dome was the atom, then in the middle of the dome, we would find the proton, and it would be approximately the size of a head of a pin. So that would be the proton, the teeny head of a pin. So the proton is really small. Okay, this is all to tell you how small the proton is and how much of a miracle it is that you're here, sitting, listening to me, just in the passing. And so now that we have an idea how small the proton is, if I were to take a Planck, which is 10 to the minus 33 centimeters of Planck length, and make it the radius or the diameter of a grain of sand, okay? A grain of sand is already pretty small. Like on the Earth, it's really teeny. You can't see it, right? Okay? And if I was to say, okay, well, here's the Earth beside the sun. The sun, you see it's flying by here? It's really teeny. It's really teeny thing. That's the Earth. So now the grain of sand on the Earth, right? And the Earth beside the sun. Then, if the grain of sand was a Planck, then the proton would be approximately the distance between Alpha Centauri and the sun, which is 40 trillion kilometers. So when people say, but I'm not feeling the Plancks, I'm like, dude, you're not going to feel the Plancks. You just, I mean, if you're psychic, something, you know, maybe somehow you got in there, but like, it's not the typical thing, oh, dude, these Plancks are in my way. They're not so obvious. In fact, you know, imagine a bubble the size of 40 trillion kilometer, right, diameter, this bubble, and you're putting grains of sands in it. How many would fit in there? That's inside a proton, right? So, you know, this is way below the typical experience you have. So, of course, when they renormalize the electromagnetic field, the Planck, you know, remember they cut off the electromagnetic field at the Planck distance? Okay, when they did that, then they were able to calculate how much energy there is in a centimeter cube of space, how much of the electromagnetic fluctuation of the little Plancks there is in a centimeter cube of space. Well, you know, we just saw how many grains of sand goes in between here and Alpha Centauri, so you can imagine that's inside a proton. Forget a centimeter cube of space, right? So in a centimeter cube of space, a lot of little Plancks go in. And because each little oscillator, of course, because of E equals mc squared, right? The energy is equal to this energy. To this, you can transfer the energy of the little oscillator into a mass, right? You can express it in terms of 10 to the minus 5 grams. That's the mass of one little Planck oscillator hanging out down there in the very, very, very small, right? It's oscillating really fast because that's a lot of mass from one little teeny weeny bitty little Planck, okay? So you calculate that and you end up with 10 to the 93 grams per centimeter cube. 10 with 92 zeros. So let me help you with that. You might have noticed in your bank account, when you add zeros, things improve rapidly, right? It's, you know, exponential, so it's like 1 0, you have 4 zeros, it's okay. You have 5, it's better. You know, you got 6, it's like, wow, you know. You got, you know, 7, whatever. 93, though, is a lot of zeros. So how dense is this stuff that you call space, then? Well, if I took a centimeter cube of space and put all the stars in the universe in it, there's billions of stars in each galaxy. I take all the galaxies, there's billions of galaxies, I stick them all in a centimeter cube of space. Imagine how dense that would be, okay? That would be 10 to the 55 grams per centimeter cube. I'd still be missing 39 zeros to make it to the vacuum density, to the amount of electromagnetic energy in a centimeter cube of this stuff we call nothing. We call space. So, in fact, matter might be a little space in the space, right? A little boundary that kind of pushes some of the Plancks into different density, right? The space may be denser than the matter, is what I'm telling you. Meaning that what we call matter or energy or mass may be just a little bit of energetic leak off the Planck field, which is otherwise smooth. So that over here, it's like organized, like the Plancks are like all kind of oscillating together nicely. And over here, they're more like, you know, hanging out. Because you got to realize as well that the Planck's constant from which all this is based on is called a quantum of action, which is an angular momentum, right? It's h over 2 pi. So it's actually a little rotation. These little Plancks, when we say a Planck oscillator, this is one of the issues that occur, is everybody visualize an oscilloscope that's going like this, oscillating, right? Everybody visualize going up and down, oscillating. But in fact, it's going like this. And the wavelength of how long it takes it to go around is a Planck. You see? The radius. It's spinning. These are little spinners. The whole thing is spinning. You might have noticed. If you look everywhere a little bit, the Earth's spinning, the Sun's spinning, the galaxies are spinning, shit seems to be spinning. Everywhere. I used to have arguments about that with physicists, you know, because they would say, oh, but the Schwarzschild solution predicts a non-spinning black hole. I'm like, dude, your equation is missing spin, not the universe. It's spinning out there. Your equation doesn't have it in there. Doesn't mean it doesn't spin. So I was like, okay, the vacuum could definitely be something significant. But this thing is so dense and it's so huge number that in general it's ignored. That's the thing. Almost 100 years of ignoring this number. And that is, when I publish papers, you know how you write physics papers, you go, okay, so utilizing the vacuum density, 10 to the 93 grams per centimeter cube, we extrapolate, right? And then I got like hate mail from physicists all around the world, like people like very qualified. I'm talking like head of department and stuff, like very qualified people saying, you know, where did you get that number? It's crazy. That is not the density. I'd be like, dude, here's the Wikipedia link. It's like, it's in every physics book, you know, like, this is fundamental to quantum physics. Like, without the vacuum density, without that Carter value, I mean, everything falls apart. And, you know, this was a while ago. I mean, now it's becoming more and more clear that this is very important and very fundamental. Most of our advanced particle physics are based on this so-called Higgs boson, you know, that is actually a non-zero value of the vacuum. It's, you know, starting to like dawn on them that they can't just ignore that number. But you know, in general, professors in schools skip over it because it's kind of embarrassing. And they know that if they say this to students, the students are going to go, wait, because they're bright new minds, and they go, why are we drilling holes in the earth, like, to get energy? Like, you know. Because we extract 1/1000% of what's there, and we run the planet for thousands and thousands of years. Like, there's more energy in a centimeter cube of water, you know. Now, you don't need the water, just the space. Right? So, But we're living on a planet where people are going, oh, we don't have enough energy for everybody. We go to war for it, right? We live in an extremely energetic universe. Now, the other thing is that people may say, well, is this for real or is this like just theoretical craziness? Well, it's been verified. I had all sorts of problems with that earlier on, you know, before the Casimir effect, before 99, until 90, before, late mid-90s, because there was a man in 1947 that called Casimir, a physicist, that said, well, maybe we can measure to see if it's really there. And he came up with an experiment where he would get plates really, really close together theoretically, and then calculate how much of the long wavelength of the electromagnetic field he could eliminate between the plates, and then because there'd be more vacuum energy on the outside and less in between, the plates would get pushed together. The plates would actually get work done by the vacuum, right? But the thing is, when he did the calculation, the plates had to be microns apart, and nobody could mill microns of plates with micron precision at the time in 47. No way. Never mind the electrostatic problems and all this stuff. So it took till 1990 till, the experiment was done. And then when it was done, it was confirmed. So the plates got pushed together exactly how Casimir had calculated they should. And, it was repeated many, many times. And now we have even better, we have little instruments that allows us to oscillate the plates very, very quickly. It's called a dynamical Casimir effect. So they're actually little piezoelectric mirrors that are oscillating, and they can get them going really fast, and they're basically pumping the vacuum, and the result is that photons emerge out of the vacuum. So we're literally already getting energy out of it. It's not much, but it's still energy. It's still work, right? And so we know it's there. Now we know it's there for sure, okay? So it's not just theoretical concepts, and we're not all just delusional, okay? So is it there at all scales? Yeah, actually. Our standard model of physics describes the universe as an expanding universe. It's typically described as a balloon with pennies glued to it. The pennies are a representation of the galaxies, and as the balloon expands, the galaxies move away from each other, and that's the expansion of the universe we observe today. Now, very early on, I went to physics conference and in private physics meetings in institutions around the US, and the question I would ask would be this, because I would tell them, I've been looking for this equation everywhere in all the textbooks, everywhere, I can't find it. Can you guys point it out to me, because I really would like to understand this better, and I want the equation, or point out the equation that I must have missed that says, who's this guy? Because without that dude over there, nothing really happens with the balloon, and the pennies and all this, kind of not happening. So if we don't have an equation for this guy, it doesn't really matter the rest of the equation. And usually it was a pretty embarrassing moment, the whole room would become silent. And what I would say is, well, if the universe is expanding, then something must be contracting. And, the air in there must go in the space in there to expand the balloon. So there must be something in the space that's expanding the balloon. Of course, since then, I was very happy to see that. I was still in the van at the time when that was discovered. It was found that the universe is not just expanding, it's accelerating. So it's not slowing down, which is, you know, if it was entropic, it should be slowing down, but it's not. It's accelerating, right? And so in order for the universe to be accelerating, and to be accelerated in our equation, they had to add what's called the cosmological constant, or they had to add energy in the balloon, and they eventually, you know, concluded that that energy is actually the vacuum fluctuation at the quantum level that are expanding our universe. So not only are we measuring it in laboratory, now it's called dark energy, or the vacuum energy is the source of the expansion of our universe. So it's really kind of amazing in the sense that we are, you know, finding it at the cosmological level, and we're finding it at the quantum level. The problem is that there is a very important problem, is that at the cosmological level, in order for it to expand our universe, we can calculate how dense it is, and it's 10 to the minus 29 grams per centimeter instead of 10 to the 93 grams per centimeter. So it's like 122 orders of magnitude smaller than what's predicted at the quantum level, and thus the vacuum catastrophe, as it's been coined. That is, it doesn't agree. Cosmology, again, doesn't agree with quantum theory. Quantum theory says it's 10 to 93 grams per centimeter cube, and cosmology says it's 10 to the 29 grams per centimeter, to the minus 29 grams per centimeter cube. So it's very low at the cosmological level. It's very not dense, but it's very dense at the quantum level. This is as well been coined the greatest error in physics. The most embarrassing predictions of physics as well. You know, many different descriptions. I resolved this, and I'm going to show you how. It's actually really, really simple why it's like that. And you'll see. So anyway, it's seen at the quantum level and at the cosmological level. So I, with the help of Dr. Rauscher, I started to write scaling laws to try to see if literally space is dividing itself in harmonic relationship that I could find, you know, in the universe, right? And so I plotted data points on the radius and the energy of a system, right? So this is the radius, this is the energy. And I started with the universe. So did you know that if you put the mass of the universe, which is approximately 10 to the 55 grams, in the bubble of our universe that we see today, the universe obeys the condition of a black hole? We live inside a black hole. Okay? And that might kind of shock you. But actually, I believe that's exactly why it's black at night. You laugh, but there's enough stars in the universe that it should be completely white, right? But the thing is, you know, if you plot quasars, which we know are black holes, and galactic centers, which we know are black holes, which I predicted they should be before they found, and stars, or, you know, stellar objects that are black holes, you know, because stellar objects produce black holes, and then atoms, and then the Planck is way over there. Look, between the atom and the Planck is almost the same distance between an atom and a star. It's longer, actually, right? So, you know, they all kind of line up. There's no reason it should do that, right? It should be all over the place, but it's not. So it started to point out that maybe everything in the universe is just different scale black holes. Like what we call a black hole is a division of the structure of space. The Schwarzschild condition, that means the condition of a black hole for the universe, for the Planck. But the problem is what about the atom? Is the atom a black hole? You know, is the nuclei of an atom is a proton, a mini black hole? Well, it's not so far-fetched, you know. Protons are very strange objects. For instance, we've never been able to see any proton at any time in any laboratory at any moment, even when we collide them, that degrades, meaning that loses its energy, that radiates, that, you know, is entropic. It just is solid as can be. It doesn't do it. It doesn't, you know, it doesn't radiate its energy and stop at any point. It just keeps on spinning. It's very strange. But in order for it, and this is when I got in big trouble, I published a paper called the Schwarzschild proton. You see, I didn't want to say the black hole proton. It was too obvious, you know. I had to, but, you know, calling it the Schwarzschild proton was, in some ways, calling it a black hole proton. And the reason I published that paper is I found something kind of extraordinary. Because I thought, okay, well, if the proton is a black hole, why is it that it has such a small mass? Right? It's 10 to the minus 24. It's a very teeny mass. It's the mass of the material world. The proton makes up the mass of the universe, mostly. So why is it such a small mass? But, and I realized, wait, you know, if basically the energy that makes up everything is the space, and then the space just divides, then maybe we only see a little bit of the energy that's present. And we call it mass, we call it energy, but that's not the whole thing. That's just a portion. It's been divided, right? So I thought, okay, well, let me calculate how many of these little Plancks there is inside the volume of a proton. So I put, you know, I calculated the volume of the proton, which is very small, 10 to the minus 39 centimeter cube. It's a very, very, very small volume. And I calculated how many of these little Planck's mass fit in there. And I got the mass of the universe. Dude. I got the mass of the universe, folks. I mean, wow. Why did that freak me out? Because I was hoping there'd be enough mass in there to make it a black hole. Well, there's enough mass in there to make the whole universe a black hole. So, but think about it. The whole universe a black hole. Okay, wait. So that means that all of the mass is present in every point? And then that's when I went, right. It's holographic, right? Now that's something I already had concluded to, that it was fractal and holographic. That's why I called my theory fractal graphic universe. But like there was the equation proving it. And I remember Wheeler thinking that the vacuum structure is actually all Planck-sized little wormholes that connects everything. And that's why, like, there's this story that Wheeler woke up in the middle of the night one night thinking, I got it. It's just one electron. And it's going around everywhere really quick. And we think there's a whole bunch, but there's only one, and it's all connected, right? The reason he concluded to that is because we can't figure out where the electron exactly is. Meaning that in physics, we can if we figure out where it's going, we actually are unsure where it is in the universe. And if we figure out where it is, we can't exactly predict where it's going. And so Wheeler had this revelation that maybe there's just a wormhole network that connects all the particles that makes it so the electron is going all around and there's only one. And he called Feynman in the middle of the night, like, dude, I got it. And supposedly Feynman told him to go back to sleep. But the reason as well that Wheeler came to these conclusions, and he came long before what's emerging now, he started to think that the fact that particles are entangled, we know they're entangled. Meaning that like you can scatter on a particle and photons will go flying apart, and you can polarize this photon over there, and this photon angle will change at the same time as this photon angle, no matter how far they are. That's called entanglement. And we know it's happening because we can measure in a laboratory. And we have laboratories that have made the experiment with long enough distances that the information at the speed of light wouldn't have time to go from this photon to this photon. And it's still happening. Like when you change the angle of polarization of this photon, this other one changes instantaneously as well. And so we know like they could be across the universe from each other and they would still do that. And recently, physicists are starting to write theories, not just me, but others are starting to write theories that says actually entanglement at the quantum level is due to wormholes connecting particles and connecting black holes in the universe. Like it's like a whole web of wormholes connecting the whole thing. Thus, the connected universe. Right? Since these presentations, oh shoot. I'm good? Okay. Since these presentations are fairly short, I don't have time to go through all the slides, I just want to tell you that another prediction of that paper specifically, and this is why I was able to publish it, is that when you make the two little protons little black holes, and you calculate the gravitational force that attracts those two black holes, it's exactly the force that we call the strong force that holds the proton in the nucleus of an atom. So this was my point in that paper, and the people, you know, that threw me tomatoes missed it. Okay? It's like, calling the proton a black hole, oh my God, he's insane. It just happened that it's exactly the correct force to hold the protons together in the nucleus of an atom, and that paper was mentioning that that is not a coincidence, right? Most likely, not a coincidence. And so basically, replacing the strong force with a gravitational force would unify quantum physics and relativity, right? And so it became clear that that was a possibility. I kind of came in from the backside. I came in from the strong force, but I didn't, in that paper, explain how the proton could have a mass large enough to be a black hole, and that's why I got a lot of tomatoes thrown at me. Okay? I'm sorry. So it was this problem I'm having. I can see it in my mind's eye, The whole thing is connected. The volume of a proton is connected through the volume of all the other protons in the universe. And somehow, you know, it's the mass that we measure, the 10 to the minus 24, must be the influence of all the other protons talking to this one. Basically, the information moving through the system ends up equal to 10 to the minus 24, the mass of the proton. We're seeing the information go through. We're not seeing all the information that's there. You see what I'm saying? Because we're not inside the net, we're outside the net trying to measure it. So, so that was insane. I was like 5 years of insanity, like literally day and night trying to find a solution. How do I write an equation that describes 10 to the 80th protons in the universe influencing one proton? And then hope that by the time I'm finished with the calculation, it's nailing the mass of that little thing at 10 to the minus 24. Right? Like, improbable. Like, anybody that I talked to about it was like, forget it, brah. It ain't gonna happen, right? You're not gonna find that. But being a little bit let's just say unusual, I decided to continue with my exploration. 5 years of scratching my head, calculating insane calculations, like equations coming out of my head, literally no sleep, so many nights, right? Trying to find it, knowing it's there, but not knowing. And then when I found it, oh my God, it's so simple, so obvious. How did I miss that? Oh my God, I was almost crying. Because, I mean, it was beautiful, but at the same time, it's like, oh, took me 30 years to get to that? So what happened is that I realized, you know, I was writing these math, and you know, so I had found the mass of the universe inside the proton in terms of Planck's. You know, people think, are you telling me that the whole universe is inside a proton? I'm like, no. It's not like that. It's like if you have a CD-ROM or you have a hard drive, you can have an orchestra on it, you know, and music. But the violinist is not on the hard drive. The piano is not on the hard drive. The information is there, right? So this is not trivial. We're talking about information bits, right? And so another consequence of what I had found is that all of a sudden I solved this 122 orders of magnitude problem between the quantum world and the cosmological density, because I took the little proton and I grew it to the size of the universe. And when I did, I got the exact correct density for dark energy in the universe, for the vacuum pushing on the universe. So I solved one of the most fundamental problems in physics today in a really simple way. And it's because nobody, thank you. And it's because nobody thought of, you know, calculating the vacuum density inside a proton and expanding it. But I was still looking. So when I did these equations, I was like, okay, it's kind of some kind of geometric solution. It's got to be some kind of geometric solution. And at the same time, more and more support was, you know, there. And it's, you know, kind of like I studied more and more of the holographic principle, which is already in the standard model of physics. That is, they discovered that if they tile black holes with little Plancks on their surface, they get the correct temperature of the black hole. It predicts the correct entropy or temperature of a black hole. It's called the holographic principle. And so that was becoming more popular, and this is kind of a geometric solution. So I was thinking, wait, they're tiling little Plancks, but then I looked at the equation. You might have seen that in Popular magazine, the universe is a hologram. Are we living in a two-dimensional surface hologram projecting our reality on all this stuff? I assure you, our universe is not two-dimensional. It just isn't. Two-dimensionality exists in the mind of people, not in the universe. Okay? You put a little happy face on a piece of paper, and you say, look, it's a two-dimensional image. Well, only in your head. Because if you shrink to the size of the atoms there's nothing two-dimensional. The ink is not two-dimensional. The paper is not two-dimensional. There's only two-dimensionality in your head. And physicists write equations with these dimensions, especially in string theory, and they forget that this is just modeling from stuff that doesn't actually exist in the universe. So then they conclude, oh my God, the universe could be a two-dimensional hologram. No. The universe is most likely holographic, correct, and the Planck is most likely the pixel for it, correct, but ain't two-dimensional. So I took the little Planck pixel and I made it a sphere, of course. If it was, you know, a universal oscillator, it must be like a little sphere, like a star, like a planet, like a cell, like a, you know. And so I made it a sphere and I tiled it. I tiled it to see what would happen on a black hole, right? So I took a very common known black hole and I tiled it on there, and I saw that, like, if you tile it on the surface, there's of course a lot of them, right? And then I thought, okay, so let me get a sense of mass. So I started to think of mass of the black hole in a different way. I started to think, okay, basically I have mass everywhere and these Plancks everywhere, and basically I'm not experiencing it because it's kind of all even, but then all of a sudden there's a boundary, so now it's not even in that region, right? So then what about the stuff that's in there? Because that was not considered. So like, what about all the Plancks inside the volume? And I realized, wait, there's way more information inside the volume, because, you know, in the holographic principle, each Planck is like a bit of information. So basically, I was saying the information inside, when I started to think in terms of information, it came to me. The information inside is not able to get out. It's restricted by this boundary. It's not like the communication link is restricted by how many Plancks, how many little wormhole termination connects to that boundary. That's the only way it can talk to the rest of the universe. And I thought, that's like a pressure, that's like a bog rate, you know, in the system. That's like, that could be the mass. You see what I mean? You guys see, like, kind of an entropy on the system. So I start to think, okay, maybe it's a ratio of the inside to the outside. So I calculate how many are inside, that's R. How many on the outside, that's eta. So R over eta, and then so that's a dimensionless number, right? It's just a ratio. And then I multiplied it by the mass of a Planck, of one Planck, to get the energy or the mass of that ratio, and then give me the exact mass of the black hole. Exact. Okay? So my holographic mass equation all of a sudden equated exactly the same solution as Einstein for that black hole. And so I was blown away, and I thought, oh my God, this is incredible. because I was describing gravity completely different than Einstein. Einstein said it was smooth, and I was doing it with little integers of Plancks, little granulates. I was saying, basically, Einstein got, let me give you the analogy. If you're in a bathtub, and so you think of yourself in a bathtub or your friend or whatever, and, you know, and there is a rubber ducky, and you pull the plug, it will make a little vortex over there where all the molecules are co-moving in a coordinated manner. And because the molecules over there are not co-moving, the rubber ducky doesn't see it. But if you bring it very close or closer, all of a sudden it starts to orbit in that region of space, right? And that's very much what we call gravity. Meaning that Einstein described, you know, if you looked at the surface of the water in your tub, you see it curve. Einstein said gravity is space-time curving like that on the, you know, near the drain. Okay? But what this says is actually, well, the curvature is just a secondary effect of all the particles of water co-moving in that region of space, which is the Plancks spinning all together. So the Plancks over here, they're spinning, but they're kind of random, you know, in their orientation of spin, meaning they're not coordinated. And then, but here in this region, they're all spinning together. And that's what makes it dance here. We call it a gravitational field. We call it mass energy. But here we don't see it. See that? And so this was more fundamental, and certainly it was quantum, because it's granulate. It says that space-time is smooth only on long distances. When you get down to the fine stuff, it's really granulate at the Planck level. So I said, well, is that going to work for the proton? Because if it was true quantum gravity, it should. The equation, by the way, I'm running out of time, right? The equation was resolving to fairly amazing simplicity. I mean, this is a geometric equation, right? It's not really acceptable in physics. Physicists don't like geometry that much. But how many? 15? Okay, so this here is really beautiful in algebra because this reduced to this. That is, you can figure out the mass of a black hole just by multiplying the Planck length twice to the mass, or this for a radius, multiplied by the mass over the Planck length. So how many Planck mass? So how many Planck mass are in a mass multiplied by the Planck length, and boom, you get the radius of the black hole. This is a very simple equation, very beautiful. It's like E equals mc squared kind of thing. And so I applied it to the proton, and I counted how many there is on the proton. So there's 10 to the 40th Planck on the proton. That's a lot, right? And there is 10 to the 60th on the inside of a proton. And then I solved the ratio, okay? And I multiply it by the Planck mass, and boom, here comes out the mass of the proton. Check this out. I'm using numbers, right? The number of the mass of all the Plancks inside is the mass of the universe. I'm using the mass of the universe. And I looked at the mass of the universe relative to the surface of a proton, to the information on a proton, and I get the exact mass of the proton, or at least a very good approximation of 0.0012. Like, right in there. Oh my God. I mean, I thought it was going to be, if I was in the ballpark, I would have been happy. If I was in one order of magnitude, I would have been happy. It was nailing it. I was like, yeah, quantum gravity, right? So I'm like, okay, well, this is good. And, you know, after I come down after a few weeks, you know, I'm like, I found it, right? Party! And then That was like, you know, because 5 years had gone by. You know, I was like that close, but I was still, it was nagging at me. I'm still 0.00, you know, 0.0012 off. Like, why is it a little bit off? You know, like, because I wanted it to be like beautiful, perfect, right? Because I knew at the cosmological level it was doing a perfect job. So I'm like, why is it kind of missing a little bit? And I realized doing research that, you know, there was a reason. But before I got there, I thought it was really cool because I had spent almost 20 years researching ancient civilization, and I don't have time to go through this in this presentation. But I had found that it seemed like there was really advanced knowledge in ancient civilization all around the world. And there was a lot of anomalies in ancient civilization all around the world, meaning there was very, very large objects that were moved very long distances over mountains and rivers, like 1,000-ton blocks that, you know, just hung out in the middle of the desert, you know, hundreds of miles from their quarry, right? I mean, we do lift about 2,000 pounds, 2,000 ton at this point, you know, with very, very large cranes. You know, it's a remarkable thing, and you know, it takes like a week of engineering before they do a lift, and then these immense crane that you're like that big beside them, you know, like pick up this thing, and it's usually boat parts, and they, you know, they bring it up, and then they go like a few feet, and then they drop it, right? They don't go over mountains. They don't go over rivers. They don't hang out in the desert, in the sand. They don't do that, right? So there was all these anomalies all around the world, and I felt, and you know, it had to do with mass and gravity. Somehow people at a certain time were able to defy gravity to be able to do this, and they left. And so they left symbols. And so I had studied symbols quite a bit. And when I looked at my equation, I realized my equation was not true if I tried to put the Plancks adjacent to each other. That is, if they were tangential, they were not correct because there was a space in between, so the surfaces didn't add up. So if I did this with my equation, it was wrong, like by orders of magnitude. Way wrong, right? And so and actually this is why this solution wasn't found before, I believe, is because they were doing cubes, Planck squares, two-dimensional squares, so of course it didn't add up. But actually the equation was true if all the space was taken by the Plancks. And this is, you got to realize we're still not talking about little billiard balls. They are little fields of energy, just like when you throw rocks into a pond, you know how the waves can intersect and not destroy each other. They are intersecting like that, and you know, and this symbol just happened to be all around the world in many different cultures, described as something very significant, something that was fundamental to creation. In fact, in the Forbidden City is just one of the examples. The foo dog at the entrance of the city is the guardian of knowledge in the traditions. And it guards the knowledge under its paw. And when you look under the paw of the guardian, you find the pixelation of the spheres just like that. Just like the equation, like literally give me the solution for mass and gravity. So I thought that was cool. But I still had this 0.0012 nagging little inaccuracy. And I wanted to solve it. So I extrapolated the geometry to algebra again, right? So I could get out a radius as well. And so this is the algebra, the solution for the proton. So 4 times the Planck length by the Planck mass over the mass of the proton. And I realized, oh my God, the mass of the proton is very well measured, but not its radius. So if the radius that I was utilizing, which is the standard radius of like the codata radius of the proton, was a little bit off, it would make my mass a little bit off. And then I took my courage and I said, okay, I'm going to tell them that the radius is wrong. Because there was controversy about the radius, because we could measure the mass of the proton very precisely, but not its radius. So I said, actually, I'm going to predict what the radius of the proton should be exactly using its mass, because we can measure it precisely. So I made the prediction that in the paper, that the radius of the proton should be exactly this, based on my theoretical tenets. And I was confident as well, because the equation worked for cosmological size object, and as well it predicted, as I told you before, not only the strong force, but the range of the strong force. It predicted all kinds of stuff exactly. And when I used my predicted radius. When I used that predicted radius, everything came out just right. Okay? For the strength of the strong force, for its range, for, you know, what's called the gravitational coupling constant, and all this stuff. So I'm like, this has got to be it. So I put it in there as a prediction, and I'm thinking, okay, it might take 10 years, 20 years. I might not be alive by the time they measure the proton more precisely than they have it today, and either prove me right or wrong. But lucky for me, there was angels, okay, looking out for me, because I published my paper the 20th of December or 21st of December 2012. Just happened that way. Actually, I sent it to the Library of Congress then. And on January of 2013, just a few weeks later, a new measurement of the radius of the proton, more precise than any other measurement done before, was published. And the value was given, and I jumped on it and calculated. And sure enough, now I was within 0.00036 of the value of the radius of the proton. But most importantly, I was inside the margin of error of their experiment. That is, my prediction may be precise, and they're getting close to it. So that was really kind of a big blow to the standard model of physics, because they're off by 4% now. And I'm on. So that means that this theory that predicts a connected universe, a holographic universe, is actually the most precise theoretical prediction of the radius of the proton, the nuclei of all atoms, the mass that makes up our universe, than any other theory on the planet today. So are you folks out there that says my stuff doesn't add up? Take that. This problem in physics has been documented on many covers of magazine. The teeny particle, big problem. The Hubble proton is nothing like we expected. No kidding. I think this was Scientific America, the proton problem. Could scientists be seeing signs of whole new realms of physics? Absolutely. And you know, this leads to a whole new model of cosmology. I gotta get to the end of this. I'm really sorry, but I'm gonna have to go fast now. A whole new model of cosmology that leads to a completely different way of seeing the world. That is, we can now describe the Big Bang as something completely different. That is, a proton escaping our universe, all of a sudden entering a vacuum density in a larger universe that's much lower, so it inflates, you know, extremely rapidly and produces a universe like us, which is what I proved in that solving of the density of the vacuum from cosmology to quantum physics. Remember that expansion? So you can visualize actually universes fizzing new universes out as it loses proton, producing new ones within it, new protons within it. And it's just an incredible thing, because in that paper that we're writing today, we actually are able to cite Einstein 2013. Because many people don't know, but Einstein published a paper in 2013. It was a paper that was lost, and that was found in 2013. And that paper was published then, and it's an exploration of Einstein trying to find a new solution to the Big Bang, in which the universe is a steady state universe that produces protons on the inside out of the vacuum and expels protons out on the outside. And so actually Einstein is supporting that view from 100 years ago, you know, or so. And you know, of course, this leads to the papers we're writing right now about consciousness that we just presented, describing the brain much more as an antenna interacting with this vacuum fluctuation, this information at the, you know, that's present at the quantum level through the microtubule structure which Penrose and Amarov had already identified. And you know that this scaling of the same network, you know, from, you know, that's the brain cells, that's universe, like the superclusters in the universe, and this is the vacuum fluctuation of the Planck. Like all, you know, basically we're looking at everything is connected through this fractal network of wormholes across the universe, and you're part of that network. And that's why I'm writing stuff on consciousness, because I think it's important as well. You know, it's like, this is not just physics that's happening over there. This is what you're made of. You know, you're connected, like literally all the information of every point in the universe is in every point of your body. Literally. And it starts to be able to explain things, psi phenomena, like why somebody can, you know, have a remote viewing experience of something that's way over there that they've never been to, or all these things. It's because the information is present. You have access to it, right? So now we can start to understand this, and that's why I was saying the spiritual stuff is most likely the physics we haven't understood yet. But as we describe these new physics, all of a sudden it starts to make sense why people can remote heal and do all this stuff, right? So, and this leads as well to incredible technology, and I will be finishing because otherwise they're going to pull me off the stage by the ankle. You know, this leads to new technologies that are emerging, and you know, this is not 100 years from now. This is like emerging now, like this new solution to gravity is a direct path to control of gravity, to be able to modify gravity so that we can lift off, so that we can bring our civilization to living as a universal civilization in space, in the galaxy, not stuck to the surface of a planet, because that is not an appropriate place to live. Societies cannot survive on the surface of planets for that long. They grow too big, their resources are reduced. Eventually, they have to get off the surface. The surface is like a nest of a bird, you know. At the beginning, it's nice and cozy, but like as there's too many birds in there and they get too big, if there's a little wind, like it's, you know, you gotta learn how to fly. And we're not gonna get there burning fossil fuel. We're just not. It's just not gonna happen. So new technologies are emerging. This is the EM drive that actually produced thrust by pushing against the vacuum. There's actually nothing coming out of the thing. It's like a closed can with microwaves in it. There's more dense microwave on one side and less on the other, and it makes a gradient that makes it push. Was just tested by NASA, you know, and there's Finland laboratories that were able to spin superconductive disk and make a gravitational beam that they can measure a kilometer and a half away, where the transmission of the beam is going at 64 times the speed of light. These things, gravitational control, these things are not generations from now. They're imminent. It's going to change your world. It's going to rock your world when you're going to Jupiter for the weekend, bro. And so this is on its way, and this is why I'm talking to you. I mean, of course, my laboratories have been working on a device similar to this, which I got incredible results very early on, including results that show that it has a positive effect on life. Because, of course, if you're getting, you know, the Planck field where it's incoherent to all of a sudden become coherent, if you get the smoothie going good, you're made of that smoothie too. So you're like, when you're close to it, it's like, ooh, I feel energized, you know? Your little Plancks are like, yeah, it's coherent around here, right? So it's technology that actually can lead to like extension of life, can lead to like incredible things. Incredible things. This is the next step for our evolution. We learn to control electromagnetic fields. Now we learn to control gravity. And it's going to change our world. It's going to change the way we do everything, the way we think of ourselves and the way we think of each other. And eventually, you know, the way we travel in the universe. So thank you very much for everything. Thank you so much, everybody. Thank you. Thank you. Thank you. And if you get a chance, and if you want the details, and you want all the reference, and you want to be able to dig into that stuff, and you want to learn more, go to our website. Go to the Resonance Academy. Okay, our website is resonance.is. Go to the Academy site and register with our delegate program. It's like a 12 weeks program. I get on there every month for 2 hours, answer questions and all this. It's awesome. It's all in there. So keep with it, guys. We're going to do it.